Welcome back. In this next video, we're going to talk about all of the different conformations in which a cyclohexane, cyclo meaning it's a cyclic structure, hex meaning we have 6 carbons, so 6 carbons which are bonded in a ring, are going to configure themselves in 3D space. When we draw a cyclohexane as a hexagon, it suggests that it sits completely flat on the page, but it actually doesn't. And it actually will arrange its molecules in what we call a chair conformation. And we're going to talk about what chair conformations are, how do we draw them, and some important ways in which we try to understand which chair conformation is the most stable. So to go ahead and start, I'm going to go ahead and maximize me here. I have here a model of a cyclohexane. So we see that we have a total of 6 carbons, which are my black, that are existing in a ring. So they're all bounded in a kind of hexagon structure there. When I take this and I rotate this and look at it from the side, you'll notice that this is not completely flat. Get my hands out of the way. You'll see that this is kind of puckered a little bit. So, for example, this carbon right here, that's headed in the back a little bit, that's kind of facing downwards, and this carbon right here is actually facing a little bit ups. And we call this a chair because if you think about this, if I was a really tiny little person, I could put my head up here, and then my body, and then my legs down on like this side. So it's like a lawn chair that I can kind of lay on, which you can kind of see on the Moodle page, kind of a cartoony diagram of that. What we're going to do is we're going to talk about how do we draw this type of structure, as well as what are all the different components. So we see there's a bunch of different colored here. Those are going to correspond to very specific positions and some new naming system that we're going to learn. So let's go ahead and start with that naming system. So of all of my different atoms that are going to be attached, each carbon on my ring is going to have 2 attachments. I have 2 that are already going to be part of the ring, so I'm going to have 2 other things where I can put an atom. That atom can be a hydrogen. Most of the time it's going to be a hydrogen, but we can also put other atoms. So we can put any type of functional group. We can put bromines, chlorines, fluorines. We can put more carbon stuff. We can put alcohols. You name it, we can put it on a ring. And it's going to exist in one of 2 positions. And overall, each of those 2 positions are going to also have directions associated with them. So there are going to be up and down directions, as well as what we're going to call axial and equatorial. The axial and equatorial are denoted here based on the kind of colors. So on my chair, you'll notice that there are 6 parts that are colored red, and those red are corresponding to axial positions. So this one right here, for example, is axial, and it also is going to have a direction with it. And here we see that it is going up above the ring, so we're going to call that axial up. Where if we look at this one right here, this one is also axial. It is directly vertical. That is what our meaning of the word axial is. However, this one is actually going down below the ring, so we're going to call that axial down. And overall, you see that you're going to have a total of 3 axial ups and a total of 3 axial downs. And these are going to alternate. So if I start at an arbitrary spot, which let's go ahead and start maybe like right here, for example, I have an axial up. If I go clockwise around this ring, axial down, axial up, axial down, axial up, axial down, back to my original axial up. So the adjacent, the very next carbon away from you is going to be the opposite direction. The other position is going to be spread out because these are going to try to conform to a 1095 bond angle, and that's why it actually folds up into this chair rather than sitting flat. If it's at flat, it would be a 120 degree angle. So by kind of puckering a little bit, it's able to maintain that 1095 bond angle, and it has very little strain associated with it, which makes this a stable system. The other position, which is going to be our equatorials, which is a word I struggle to spell. Equatorial. we'll see that there are a total of 6 equatorial positions, which are denoted by the E's. And each of these are also going to have a direction. So if I look at that top E, that is going to be going downward sloping. So we're going to call that equatorial down. And then if I look at my lower E, that E is going up sloping. So we're going to call that equatorial up. And similarly, as I go around my molecule, I'll have an equatorial down, equatorial up, equatorial down, equatorial up, equatorial down, equatorial up. Now, it is really important when you're drawing a chair to actually have the correct and unambiguous drawing of that type of position. Axials need to be vertical, equatorials need to be slanted. If you have things that are kind of like out in limbo, where let's just kind of show in black, if you have something that's just kind of like shooting sideways way out here to like a hydrogen, we don't know what that means. And it's really hard to make an assessment on what that actually is. So you want to be really discreet and very particular with how you draw your rings. And we're going to get a bunch of practice with that in class. Now, one of the big things that we're going to be doing is most of the time we're going to be taking a cyclohexane into this kind of like flat structure that I drew originally, and then converting that into a chair conformation. And that's like the actual conformation that molecule exists in 3D space. There are going to, though, be 2 different variants which we can draw, and we're going to call these chair flips. And for almost all our molecules that we're going to draw 2 different chair conformations. And these are going to be just kind of like swaps or flips of each other. And often one of them is going to have higher amounts of stability. And we're going to be going through and assessing which of them is most stable and therefore is the one that's going to exist the most. And there's going to be an important term, which we're going to call 1,3 diaxial interactions. And 1,3 diaxial interactions are going to be things that are going to destabilize or make our structure not stable. Now, in our axials, so for example, I have an axial up here, an axial up here, and an axial up here. There is going to be some amount of steric interaction, just like how when we were thinking of like our Newman projections, we don't want things eclipsed. Having Gauss is better. Having all the way far away anti is the absolute best. Kind of the same idea here. You want your big groups to be as far away as possible because there can be some clash between your groups that are in the axial positions. And we call these 1,3 diaxial interactions based on where they are on the molecule. So for example, if I call the leftmost A, that axial up position 1, my second position could be either clockwise or counterclockwise. So this in case I'm going counterclockwise. My 3 position would then be 1 away. So those 2 right there are at like a 1 and a 3 position on our ring. And then you also then have like the other one, which we could call like a 5 position. So you'd have 1, 5 and 3, 5 as well. But we just summarize that just to the lowest amount. And these 1,3 diaxial interactions are going to be ones that are going to be the most destabilizing. Now, one common misconception is, why don't you see interactions on your equatorials? If I look over, let's grab maybe a different color. If I look here at this equatorial and this equatorial, on the paper, those look like those are really, really close. A lot closer than, for example, some of my axials. So you might wonder, why don't you have big issues with those equatorials? And that's actually just because of how we draw it in space. So if we look back at our model kit and we look at how close these axials are, they're pretty close. They're a normal bond length is here, so it's about 2 bonds away. If we look at our equatorials, these are actually really, really far apart. So here's my equatorial up, and then here's my equatorial down. You'll see that those are actually really, really far apart compared to just your distance between your 2 axials. So your equatorials are going to be more stable positions, So often if we have a really big bulky thing, we're going to want to put it in the farthest, or we want to put the big stuff in our equatorial positions because there's going to be more room there. Let's go ahead and get a little bit of practice with numbering our systems and then drawing a ring flip. And we'll probably end the video after that. So here are two different examples of a ring. And in our next video, we're going to get a bunch of practice actually going through and drawing rings. One important thing is kind of tracking what carbons correspond to what in our two different ring structures. Let's go ahead and start with an arbitrary, let's go ahead and start with this one, and let's go ahead and call this position number 1. You can call any position number 1. It's a circle. Normally you'll call whichever position has your other stuff attached to it. So your not hydrogen things. A lot of times we're going to have like a carbon or a bromine or a chlorine. That's often where that is going to be our number 1 position. Once you define a number 1 position, and at this point, because there's no attachments, you can choose whatever position you want. You're going to go in and you're going to number everything clockwise. So my number 2 position would be here, 3 position, 4 position, 5 position, and 6. In a ring flip, what we're doing is we're taking our position or we're taking our ring and we're kind of just doing a little jimmy. We're just going to kind of rearrange it a little bit. And what we're going to do is we're going to take this number 1 position and we're going to push it up. And then we're going to take like this number 4 position and we're going to pull it down. So in our ring flip, my 1 is now up on the top, which is going to be right here. And as a consequence, I'm going to continue to count clockwise. So my number 2, when that 1 comes up, it's going to push that number 2 to kind of be down in this like elbow spot. So that's going to be my 2nd, my 3rd, my 4th, which is now all the way at the bottom, my 5th, and my 6th. And it's important to kind of understand where things go on our rings. Now, on any arbitrary position, you're only going to have 1 axial and 1 equatorial carbon, and there's only going to have a very specific direction of up and down, and they need to be different. You're never going to have an axial up and an equatorial up on the same carbon. You're always going to have 1 axial, 1 equatorial, 1 up, and 1 down. The question is what combination you're going to have. We'll get a bunch more practice with this in our next video, but let's go ahead and just get a little bit of a preview here. So if we look at our number 1 position, our number 1 position is kind of looks like it's almost like an arrow kind of pointing downwards, and that's going to be our direction of our axials. So my axial, which I'm going to go ahead and maybe just call A here, is going to be some group that's going to sit in an axial down position. My other group, therefore, can't be axial, so it must be equatorial, and it can't be down, so it must be up. So we're going to draw an equatorial up for my other group, which in this case, I'm just going to call B. In my ring flip, when I move it, all we're going to be doing is switching all of the axials to equatorials and all the equatorials to axials. We're not going to change the direction. If you were up in the original, you must be up in the final. So if I look at my new ring, I have my 1 in the kind of top left now. Of this is kind of pointing upwards. So my axial is actually going to be an up, and then I have an equatorial that's going to be down. And in my original drawing, B was the thing that was up. So B is going to be the thing that is up. A was the thing that was down. So A is going to remain down. So we'll see my B in my original structure is going to be an equatorial up. In my ring flip, it is going to be an axial up. In my original one, my A was an axial down, and it becomes an equatorial down in the ring flip. In all of our problems, we're going to go and we're going to draw both of these, and we're going to populate it with all the things that are going to be attached. And we're going to be thinking about which of those is going to be more stable. And we're going to draw our, or represent the stability by our arrows. And we're going to show that these are in equilibrium, which is going to be the 2 half arrows pointing in each direction. If those have the same amount of stability, we're going to draw those as equal lengths. So in this case, this is drawing and saying that these 2 are equal. if they're unequal and one of them is favored, so for example, if our right one is favored, what we're going to do is we're going to draw an unequal equilibrium arrow where one of them is going to be longer than the other, meaning it's going to be favoring one side. So hopefully in this first introduction to rings, you see that we have this interesting type of structure known as a chair. It's going to be made up of axial and equatorial positions, which are going to be alternating up and down throughout our molecule. We are going to be drawing two different chairs, which are going to be the same structure, just in a different conformation. And the reason we're drawing these two is to understand which of them is going to be more stable, and the one that's going to be the most stable is going to be the one that has the minimal amount of our 1,3 diaxial interactions. We're going to stop there, and I will see you in the next one.